So I guess before I get started, are there any questions? As before, um, the lecture notes are already typed up and they're online. And the thing I like to say about the lecture notes are that they're going to change as we go through them, as we find typos, bugs, errors, things like that. So um, I would not recommend printing out the lecture notes. It's good to have them on hand as an electronic copy, but printing them out may be a little bit ill-advised. So those will change constantly. As we go through the slides, if we find some typos, I'll go back and change those and update the slides. But I try to have the slides for you ahead of time so you can write on them. That's kind of the idea. So you can make margin notes, and if you have a piece of paper nearby, like I do, you can make notes on a paper, how whatever is best for you. I know that sometimes I tend to go a little bit quickly because I'm covering notes that I have typed out in slide format. So if you want me to slow down, you can also let me know and request that I slow down, and I'll be glad to do that. So a little bit about the class mechanics. Of course, the course is about multigrid methods, but I think you probably want to know a little bit about how the class is going to operate first. Of course, it's all online. Couldn't find a room for this place because of the time change, but that's okay because a lot of my classes have been migrating to a pretty strong online component these days. Um, the class is basically organized around attendance, so please attend lectures and also participation. So participation is going to be or come in the following form. I'm going to ask you to read the notes, look at the slides, let me know if you see any typos, if there's something that's hard to read, difficult to understand. I'd like to know about it so I can make some changes. I'll also, at the end of the chapter, or maybe even before, ask you guys to work out some problems. And at the end of every chapter, there's going to be five, six, seven problems, basically stuff that I've covered in a lecture, but I didn't take time to prove. So facts that are not necessarily self-evident, but require some computations and a little bit of time and effort to go through and to realize. I don't care how you get through those problems. So if you want to work together to solve problems, I'm perfectly happy with that. Um, you can, they'll never be collected. So there's nothing to turn in. There's no quizzes. There's no exams in the course. So I'm simply going to ask you guys, did you look at those problems and did you find any difficulties with them? And hopefully you'll say, yeah, we broke them up and we this group took this problem and this group took that one and we solved them and everything works out. So my worst nightmare is to be or would be for me to assign a problem to which there's no solution or say something is solvable or say a formula is true whenever it's not true. So that's the sort of thing examined at the end. If you want to write something up, then that would be great. No problem there. Um, but it won't be collected. If you want to send it to me by LaTeX or handwritten, I'd be glad to look over your solution and give you some feedback on it. Okay, so that's how it's going to operate. Pretty low key. I hope that everybody learned something. But the thing is, there's a really good chance. There's a really good chance, and a not. I would say there's a really good opportunity for you to learn nothing in this course. Let me put it that way. There's a really good opportunity for you to learn nothing because I'm not really giving you tests, quizzes, because I'm putting all my effort into writing these lecture notes and the slides and things like that. And I'm giving it to you, hoping that you study it, that you profit from it. But if you don't put in the effort, then you won't get as much out of it. So That's just my little word of warning. And by the way, now that I'm thinking about letting me turn off, there we go, do not disturb. Yeah, there we go. Don't want to get any text messages from the mailman or whatever. Okay, so multi-grid methods, a mostly matrix-based course. So I want to talk about multi-grid methods in this course. And multi-grid methods are a acceleration tool for what we call classical iterative methods. So if you took my course, and most of you have from this book, we talked about classical iterative methods in there, like the Jacobi method, Gauss-Seidel, Richardson's method. We talked about other methods, which I wouldn't call classical, which are called under the title of the Krylov subspace methods. It's another class of methods. But the way multigrid should be thought of is multigrid is kind of an acceleration technique for the Jacobi method or Gauss-Seidel method. And so that's what I want to explain to you. I want to convince you that it works and then also give you the theory of why it works. And then we want to get our hands a little bit dirty by looking at some codes and some examples and things like that. So some proof of concept that it works by doing some computations. That's the idea. So chapter 1, this slide deck, as I said, is available on Canvas. Hope you all grab a copy. This is part 1 of 2. So we'll have 2 slide decks, roughly 70 slides each, which is going to cover chapter 1. I usually take, for something like this is something like 70 slides. It'll take me 2 to 3 classes to get through this. So chapter 1 will take 3 or 4 classes in total to get through. Okay, so 2 slide decks, 3 or 4 classes, and that's how things will go. So let's start talking about classical iterative methods, the subject of chapter 1. Well, the first thing is, why are we doing this? Why are we interested in classical iterative methods? We're going to be solving linear systems of equations, something like this, AU equals F. So typically I would write AX equals B or something like that, but this is kind of evocative of what we're doing when we're studying PDE. So A is our linear operator. This is a square matrix. U is the unknown vector, and F is the known forcing vector. So now we're going to be studying a specific class of these linear, at least to start with, linear systems of equations. And they're usually going to be derived from PDE problems, like the Poisson problem, minus Laplacian of U equals F. And the way they're derived from these problems is, well, let's suppose I want to solve this on a square domain. So omega is a square. So I'm going to do what you would normally do in problems like this. The first thing you might try, the simplest thing, is you would break up the domain into a grid of points. And you could either put the unknowns at the vertices or maybe at the cell centers. Okay, and here. So the idea is now I've got a discrete number of points, a discrete number of values that I want to solve for. Well, these become the values that I transport or transpose into this vector U. And somehow I'm going to discretize this operator, maybe by the finite difference method, maybe by the finite element method, so that the process of discretization in the end leads me to a linear system of equations, AU equals F. So this is to be, again, evocative in the sense that A is my operator. That's pretty typical for a differential operator, even in the abstract form. U is the unknown. So the reason people called it U is U was forever related to the displacement, and U was the displacement vector in mechanics, and F for forcing. Okay, so operator, displacement vector, forcing. And the same thing down here. Operator, displacement, not vector anymore, but displacement function and the forcing function. We discretize this, we get this linear system of equations. But it turns out we might have not the simple grid of unknowns, we might have a very dense grid of unknowns. Maybe we've got 1 million nodes in each direction, so we've got 1 million squared unknowns to solve for. So this makes this problem extremely difficult because the number of unknowns is very large. We can't rely anymore on our simple LU factorization or Gaussian elimination to solve this very simple problem. If, if U only has, let's say, on the order of 10 unknowns or 100 unknowns, then you just should do Gaussian elimination. It's not a big deal. Or if you like, it's just the backslash operator in MATLAB. However, if you start looking at something with hundreds of millions of unknowns or billions of unknowns, then you have to make a decision. Can you still use the standard Gauss-Seidel method or LU factorization, the sort of direct approach, or should you take something a different approach, something more sophisticated? The thing is, in this course, we're going to discuss that more sophisticated option, and we're going to discuss multigrid methods as a way of solving this in an efficient way. Whenever it turns out that direct methods just fail and just can't solve this problem in any kind of realistic times anymore. Okay, so that's the subject of this course. How can we solve problems like this efficiently, quickly on a computer? Now, we can look at the system in a kind of generic way and just say, okay, well, suppose, will these methods be fairly general? And the methods are what I would say, I would classify them as somewhat general, but not perfectly general. But the methods that I'm going to discuss in this section on classical iterative methods, let's just think about this in sort of general terms. We're not going to think about this as being resulting from a discretization of a PDE. And so we're just going to put very mild assumptions on A for now. For example, we're going to assume that A is invertible at least. Most of the time in the text and most of the time beyond this chapter, we're going to be assuming that A is a little bit better than invertible. For example, we'll assume that it's symmetric and positive definite. It doesn't make sense for us to be completely general. So if you took my course in the past, you know that I like to think about complex matrices and complex n-dimensional vector space. So here we're going to stick to real land. We don't need to go into the complex numbers and the complex vectors too much. So most of the problems that we're going to discretize are going to end up with, real coefficient matrices. So let's just stick to A being a matrix of real numbers. Okay, so let's get some basic stuff out of the way first because it's the basic stuff, it's the first stuff, notation and basic facts. So again, a good reference is our book, this classical numerical analysis text. And for those students here at UT, this is freely available. I don't know if you know that, most of you do, but if you go to the library's website, you'll find a link for an electronic copy of that book. So most of this is just repeated notation from what we used in our textbook. It's more or less the same with a few minor differences here and there. So the first thing is our symbol for n-dimensional real vector space is the same as in the classical numerical analysis text, Rn. This is fairly standard. The only difference is we're going to tend to think about Rn, if we don't say anything otherwise, we're going to think about these as column vectors. That makes the most sense rather than row vectors or generic n-tuples. But generically, it's not really a column vector or a row vector. It's just the n-tuples. But as I said, it's just going to be convenient for us to think about these as column vectors. I'm going to introduce this notation, Rn star. This is always going to mean Rn with the zero vector punched out. And this is the notation I use everywhere. So if I want to use the real number, just the regular real numbers with zero punched out, I'm just going to write R star. Now, how do I write vectors? So I'm commonly going to write vectors like this, a boldface Roman letter, And if I want to emphasize what are the components of that vector, I'm going to put brackets around objects like this. This this unbolded character U whenever I use a boldface U with a subscript I. So this just indicates that I've got components which are UI, I equals 1 to n. So I know it ends in n because we're drawing these from Rn. And again, these are always understood to be column vectors or equivalently matrix having n rows and one column. Actually, the only difference, there really is no difference between a column vector and a matrix having n rows and one column. And in fact, this language of matrices allows us to think about row vectors and column vectors. So row vector is just a matrix having one row n columns and only one row. And similarly for column vectors, it's one column and a bunch of rows. Now, if I want to access the elements of a vector, I'm just going to write brackets around the vector and I'll put a subscript. And so this is like if you want to draw out what is the jth component, then, if this thing is more complicated, it might be something more complicated. But in this case, it's very simple. The jth component is just u sub j. Okay, so typically this part of the writing of vector is always understood, so I drop it. So if I want to write a matrix with m rows and n columns and components that look like that, so that's the full notation. If I want to draw out the elements of the matrix, the ijth element, this means the element in row I and column j, then of course that should be I sub j. So as with vectors, we're usually going to drop this part. And it's always going to be understood that if you want to write the components of a matrix, it should be, if there's no ambiguity, it's going to be the lowercase letter with subscripts. Okay, same notation that I've always used for those of you who've taken my classes before. Now, if I want to do a matrix vector product, matrix vector product can be defined very conveniently like this. So if I have a U from Rn, an A from, let's say, having m rows and n columns, then this is going to be a vector in Rm, and its components are precisely given by this formula. Okay, so pretty simple standard stuff. And of course, matrix multiplication can be done easily enough. If I have a matrix with m rows and p columns and another matrix B with p rows and n columns, I can form the product. And of course, the product has elements which look like this. Okay, standard matrix vector multiplication. Basically, I'm simply showcasing, or sorry, matrix multiplication. I'm just showcasing the notation that I want to use here. Okay, so transpose operation. This is all fairly elementary stuff. If I have a matrix and I want to take its transpose, the ijth element of the transposed matrix is just the ji element of the original matrix, right? I can use the transpose to define different types of products. And the way I think about this is I think about now the vectors being row or column vectors, and then just thinking about this as standard matrix multiplication. So for example, if I start out with two column vectors, u and v, and I transpose that column vector, it becomes a row vector. And so then I can take a row vector and multiply it times a column vector to get a number. So this is really just the dot product, right? Again, all elementary stuff, but showcasing the notation, how I use it. And then this object here, if V and U are elements from Rn, then VU transpose has to be a matrix. And actually it's a matrix that's n by n, and it has the elements, or the ij element, VIUJ. Okay, all elementary stuff, just showcasing the notation that I want to use. I'm going to use the following notation for the canonical inner product. So if U and V are vectors from Rn, then this object is the dot product or the inner product. But you have to keep in mind how I use this. This usage doesn't matter from the point of view of for real vectors, but it matters for complex vectors. But I'm being a stickler about it in any case. So if I put u here and v here, then when I define this object, u comes second. So that's just something to keep in mind. That's the same notation that we use in the purple book. So this object is what we call the canonical inner product. Well, the idea is we're going to create a bunch of inner products in this course. And the way we're going to create inner products is through symmetric positive definite matrices. And the methodology is fairly standard, but it's the notation that I want to get across here. Now we're going to define symmetry with respect to different inner products, and the way we define symmetry with respect to inner products is in the following way. So I'm just showing you how we do it in the standard canonical Euclidean inner product setting. We say that a matrix A is symmetric if and only if for all u and v and Rn. Notice I start off with a matrix which is square. Then in the canonical inner product, canonical means there's nothing here. Some people will put a 2 here. And the reason I'm not going to put a 2 here will be evident later because I'm going to use subscripts for other reasons. It's called symmetric if AUV equals UAV in the canonical inner product. So now what this means can be determined from this definition here, and what this means can be determined from the same definition. So this is my definition for symmetry. Your previous definition, or probably favorite definition of symmetry, was that A transpose equals A, right? And so actually that's equivalent to what I've said here, and we'll touch on that in the next slide. But I just want to show you what symmetry means with respect to a sort of generic inner product. Okay, we say that A is symmetric positive definite if and only if it is symmetric and symmetric in this sense, and for all u that is not that are not the zero vectors, u transpose AU, which is the same as AU u in the inner product, is strictly positive. Okay, so that's the pretty standard definition of positivity. Okay, suppose that A is a symmetric positive definite matrix, then we can define a new inner product from this. And so the new inner product that I'm going to define is called the A inner product, or sometimes called the energy inner product. So I probably should have said that as a separate definition, but this is something called the energy inner product or the A inner product. And the way this works is it's defined through the original inner product. And all you do is you attach the A to the first U. Okay? But if I look back here at the definition for the canonical inner product, that means that this object here is just V transpose AU. Okay? So I claim from this, I can define this new object, and it's called the energy inner product. Now, I shouldn't use the term inner product until I know it's an inner product. And you remember there are certain axioms that an object has to satisfy for it to be called a bona fide inner product. I won't go to that level of detail in this book. That's something I'll kick back to the big purple monster, and you can go back and look in the previous text and see what are the axioms for inner product. I'm sure you all can rattle them off from memory anyway. All right, so using that definition of inner product and symmetry, it's pretty easy to show that a matrix is symmetric if and only if it's equal to its own transpose. Okay? Now, how would I prove something like this? Well, remember, and don't get caught up in the fact that this is the usual thing of that you think of as symmetric. Okay? How would I prove this? Well, I would go back to this definition here, and I would simply say, what do you think I should put in for U and V if I want to show this property here? What do you think? What should I choose for U and V? Well, let's try first of all. You've heard of these things called the canonical basis vectors, right? So the canonical basis vectors are, we're going to usually use E1, E2, En for those. So those are the vectors from Rn that have a 1. Ej is defined as a vector that has a 1 in the jth position and zeros everywhere else. So I think let's try taking this object here, this fact, and putting in Ej, Ei for U and V and seeing if that'll prove it. Okay, so basically all we have to prove to show this fact is prove that Aij equals Aj, right? That should do it. And that should be exactly what you get from using that definition. Again, elementary stuff you've probably seen before. Now, before we go on, one other thing I want to say is if we're in Rn and you give me some generic inner product, and so I'm going to call that, what should I call this inner product? The star inner product. You tell me it's an inner product, um, and we're working in Rn. This, of course, becomes something we call a Hilbert space, right? A complete inner product space. But the idea is we're in finite dimensions. We're in Rn. So it turns out that there exists a unique matrix. What do we want to call this unique matrix? Let's call it Q, n by n, which is SPD, such that the star norm, or sorry, star inner product, is equal to, well, let me say it like this. The Q inner product. Okay, so we saw you can go one way. If you, and in fact, I haven't stated this theorem yet, but it is a result. If I have an SPD matrix and I define a Q inner product with that, analogous to the A inner product or the energy inner product that I defined previously, then that defines an inner product. Okay, that defines a bona fide inner product. And conversely, if I start out with just knowing something is an inner product, I can find a matrix Q, right? So that that can be written in sort of this way, or sorry, this way. Okay, so it goes both ways. If I have a symmetric positive definite matrix, that defines an inner product, and if I have an inner product, that defines a symmetric positive definite matrix. This is probably a fact that you'll remember from 571 or 572 as well. The numerical analysis one and two here at the University of Tennessee. All right, now we're going to take the advantage of the following result in a lot of times. And in fact, we will use this result, but we'll also use the generic or generalized spectral decomposition theorem that I state in our book. And I won't mention that, but I'll refer to it often. So it might be a good idea at some point to go have a look at that. It's defined in the sense of it's using Rn with a generic inner product, not necessarily the canonical one. But here, this is the standard spectral decomposition theorem where we're really referring to the Euclidean or canonical inner product. And it goes like this. Suppose that A is a symmetric matrix, standard symmetric matrix. So that means we know this also means that A transpose equals A, if you like. Then all of its eigenvalues are real. Moreover, there's an orthonormal basis. And by orthonormal, what do we mean? We mean that it's orthogonal and normalized with respect to some inner product and its resulting norm. Remember, by the way, there's another fact that we're going to use a lot. Remember, an inner product always induces a norm. So do you remember that fact? An inner product always induces a norm. So this, we're talking about the Euclidean inner product here. So that induces the Euclidean norm. And what's another name for the Euclidean norm? 2 norm. Yes. So the 2 norm is the Euclidean norm. Okay, so there is an orthonormal basis of complete basis of eigenvectors. Oops, this is a mistake here. This is a typo. This should just be Rn, not Rn by n. So there's a complete orthonormal basis of eigenvectors for Rn of A. Okay, so the proof of this can be found in our book. There's a proof for what we call the generalized spectral decomposition theorem as well. And so the generalized spectral decomposition theorem goes like this. So if A is an n by n matrix that is symmetric with respect to any inner product, okay? Just somebody tells you, I have an inner product and a matrix, and the matrix is not necessarily symmetric in the standard Euclidean sense. So A transpose does not necessarily equal A, but it is symmetric with respect to this inner product. Then what can you tell me about it? I can still tell you that all the eigenvalues are real because, and that's an interesting thing. We'll talk more about eigenvalues in a moment. All the eigenvalues are still real, and I have an orthonormal basis of eigenvectors for that matrix, but it's orthonormal with respect to the inner product that you gave me. Okay, not necessarily the standard Euclidean inner product. So that's what I call the general spectral decomposition theorem. Okay, for which this is a special case. And that can be found in our book on numerical analysis. Any questions? Okay, so a matrix is SPD, symmetric, positive, definite. Remember that meant that we had symmetry with respect to the inner product and positivity with respect to the inner product. And of course, now we know that symmetry with respect to the Euclidean inner product means it's A transpose is equal to A. So a matrix is SPD if and only if it's symmetric in the standard sense, and all of its eigenvalues are positive. And in fact, we can generalize this. We can say that a matrix is SPD with respect to another inner product, if and only if it's symmetric with respect to the inner product, and all of its eigenvalues are still positive. Okay. So that's a little theorem or result that you proved in 571. That is our first numerical analysis course here at the University of Tennessee, or that you will have proven in whatever introductory numerical analysis course you've taken. All right. Now, oftentimes we're dealing not with one positive definite matrix, but we're dealing with 2 positive definite matrices. And they're kind of siblings to each other in some sense. They're related. They're not necessarily completely unrelated, but they could be. We could just say, okay, here's a symmetric positive definite matrix, and here's another one. I multiply the 2 together. Here's a little question for you. If I multiply 2 symmetric matrices together, is the product symmetric? If I multiply 2 symmetric matrices together, is the product symmetric? Not necessarily. However, it will still be symmetric with respect to an inner product, some inner product, as long as the 2 matrices turn out to be positive definite. Okay, so here's what happens. So suppose that I have 2 matrices that are symmetric, positive, definite. And by the way, if I don't say anything else, then that always means symmetric, positive, definite with respect to the Euclidean inner product, okay, or the canonical one. Now, in fact, I say, I make a claim here. It's true. It's a true claim, but it's not the whole story. So here's the story, and then I'll give you the whole story. The two objects that I created before are bona fide inner products on Rn. Okay, they're good and true inner products on Rn. Okay, the first one is the A inner product. Remember when I have a matrix and I define it in this way, I've already defined that object, but this one's a little bit different, right? This is the inverse inner product from B. Well, let's think about it. If I have a symmetric matrix B, is its inverse also symmetric? Turns out, yes, that is true. And are its eigenvalues positive? Yes. The eigenvalues are just the reciprocals now, right? So the eigenvalues are positive for the inverse matrix. So in fact, I could say I have this whole full class of things, right? So here's one object. Is that going to be an inner product? Yes, because A is symmetric positive definite. And this is also going to be an inner product. Check. This one's going to be an inner product. And also this one is going to be an inner product. So A inverse, B inverse, because each one of A inverse, B inverse, they're symmetric positive definite. Okay. So all four of these are good and true inner products. But the thing is, I'm really only interested in these two. Okay, so they're both inner products. This should probably even be a theorem, I guess. Moreover, the product matrix BA is symmetric and positive definite with respect to either of these two inner products. Okay? With respect to either of the two inner products, but not necessarily the Euclidean inner product. Okay? Consequently, all of the eigenvalues of BA are positive. That is the product matrix BA. And there's an orthonormal basis, orthonormal with respect to either one of these two metrics that I just chose or just defined. There's an orthonormal basis of eigenvectors of B times A. Okay. And that's just an application of that general spectral decomposition theorem. All right. So how do I show that these two objects are inner products? All you have to do is check the basic properties of an inner product, the axioms of what it means to be an inner product. There's like 4 or 5. There's the symmetry property. Remember, if we were in complex n-dimensional space, then we would talk about the conjugate symmetry. But here we're just talking about symmetry because we don't have to worry about like conjugation. Symmetry, there's the positive definiteness property, there's a kind of additive property, and then there's the kind of triangle inequality property. Um, okay, so you just check that those properties hold and then you're done. But what do we mean by saying that the product is symmetric positive definite with respect to either of these two inner products? Well, let's take, for example, this one, and the A inner product can be done similarly. So what we want to do is start off with an arbitrary U and V vector, both from Rn. And so let's take that inner product, okay, and we'll put BA against U over here on the left-hand side, and we'll put V on the right-hand side or the right-hand slot. And what we want to do is show through some manipulations that I'm eventually going to end up with a BA popping up over here. And if I have this property, if the BA suddenly pops up over here with the U and V being in those locations, then I know that it's going to be symmetric with respect to that inner product. So let's just use the definition here. So remember what the definition means. I'm going to take this, according to my definition, I'm going to take this B inverse and I'm going to attach it here in the Euclidean. And then when I do the Euclidean inner product, this actually comes first with a transpose. So we get V transpose, and then I have B inverse, then I have my BA, and then U. But of course, B inverse B is just the identity, goes away. and I just get something which looks like this. But the identity can pop back up anywhere I want. So what I want to do is pop it back up over here. Okay, so B and B inverse over there. Now what am I going to do? Well, remember A and B are equal to their own transposes because they're themselves Euclidean symmetric, canonically symmetric. So A is equal to its transpose, B is equal to its transpose. Remember, now I have three objects which can be multiplied together, each of which has transposes on them, so I can take the product in the reverse order and attach a transpose. So this whole thing is BAV transpose, and I'm left over here with this B inverse U, B inverse U. Okay, so now let's put this back into our definition. So this guy is now, in my definition, going to be the second component. The B inverse goes away because we're using the B inverse inner product. And all this business here, whatever's transposed, is the second. The important part is that BA pops up over there. And this is what we mean by symmetric with respect to B inverse. Even though I didn't really define it, it should be understood that you would define symmetry for a generic inner product in exactly the same way we did for the Euclidean inner product. So this shows symmetry with respect to our B inverse inner product. But what about the positivity? So the positivity is not hard to show. You just need to start off with a vector which is non-zero. Make your definition here. So I want to show that this object is positive. I use my definition to write it out. Of course, the B inverse goes away. It hits on B and kills it. Well, they self-annihilate and just become the identity. And all I'm left with then is U transpose A times U. And why is this positive? Why is U transpose A U positive? Where did we use the fact that B is SPD, by the way? B is symmetric positive definite, and B inverse is therefore also symmetric positive definite, which makes this an inner product, which means it's useful. Okay, so now what about the other points from that we want to show? Namely that all of the eigenvalues are positive. Well, okay, so now we have to appeal, we have to do a little bit more work. This part here, the fact that we get an orthonormal basis, follows from the fact that this is going to be symmetric with respect to this new inner product. Okay, so that's what gives us our orthonormal basis of eigenvalues, eigenvectors, through this generic spectral decomposition theorem. The positivity comes from another slightly different argument, and it's an argument which is similar to the one we mentioned previously but didn't exhibit, and that is if A is symmetric positive definite with respect to the Euclidean inner product, then all of its eigenvalues are positive and it's a symmetric matrix, right? It's an if and only if thing. So that's how you finish up on those last few points. You need a generic spectral decomposition theorem to address one of the parts, but the positivity of the eigen values comes because of the positivity of this matrix with respect to an inner product. Okay. If you've taken my 571 course, Numerical Analysis 1, then you will have seen the trick. You just may have forgotten it. Okay, so that's all we need really of basic notation and facts. Of course, we need a ton more, but that's all I really want to spend our classroom time talking about. And that's because most all of you have seen it before in your first course on graduate numerical analysis. But you do need other things like you need to understand some properties about induced matrix norms. You need to know a lot of properties about eigenvalues and eigenvectors. And we'll use those pretty liberally as we go along, but we won't go back and look at them in any detail. I'll just assume that you guys remember that or know where to look them up. The facts about eigenvectors and eigenvalues and norms that we're going to use are all pretty standard. So it's not going to be esoteric stuff. It's going to be fairly standard stuff that you would you would learn in your graduate numerical analysis course and that you use, for example, in studying for the prelim, et cetera. All right, so now that we've gotten the notation and basic facts out of the way, let's talk about these classical iterative methods. And these classical iterative methods all fall under an acronym that I've given. I don't know if I like the acronym because it's not so fun to say, but I created it, and so I have to live with it for at least a little bit until I decide to kill it. So these are called general linear iterative schemes. I could call them classical iterative schemes, but the reason we use general linear iterative schemes is there are other iterative schemes out there which are kind of classical by now, namely GMRes, conjugate gradient method, steepest descent method. And so this name is just to separate the things we're going to study here from those objects, the Krylov subspace type of iterative schemes. So what is a general linear iterative scheme? So it's given in this definition. Suppose that A is invertible. That's the least amount of stuff that we need to get things working for this to make sense. Suppose that F is a given vector. F is always given. I guess in the back of your mind, you should be thinking, I want to solve this problem. Okay. So we're going to come up with a way of constructing a sequence where such that the sequence converges to the true solution U. That's the idea. But F is always given, A is given, and U is the unknown thing here. By saying that U is equal to A inverse F, that just means it solves this problem. I'll use this shorthand all the time. So rather than say U solves this problem, I just say U is equal to that vector. Assume that B is invertible and U0 is given. By the way, so for sequences in this course, I'm going to use a superscript. And that's because, well, let me back up and say, historically, I use a superscript for a time index. So you probably remember this from your second numerical analysis course or your numerical ODE or PDE course. A superscript is kind of a time index. That's the time level. So I do U1, U2, that's the next time level, U3 is the next one, and so on. But here, there's no time involved in any of these problems that we're solving. We're thinking about solving things like Poisson's equation, and so there's no time variable at all to be found. So we're safe in using a superscript as another kind of index. And the other kind of index is going to be is the index in a sequence. Okay, so that's always going to be the case. The superscript means sequential index. So a general linear iterative scheme, the GLIS, acronym I don't like because it's not fun via the recursive iteration that you see here. Zero. And then after that, I compute U2 and U3 and so on. Okay, so it's recursive in that sense. And all the blocks that I introduced earlier appear in this definition. So here's that matrix B, which is invertible, that goes there. The matrix A goes there. U0, whenever k is equal to 0, would go here, and that would enable me to compute U1. So this is what we call an explicit recursive iteration process. Okay, you can explicitly compute U1 by just doing this combination of algebraic steps on the right. The B matrix is called the iterator of the linear iterative scheme. And the error sequence is defined as follows. So if I want to compute the kth error, that's just going to be U minus UK. That's what I call EK. The residual is defined as F minus AUK. And it's not hard to show that that means that RK is equal to A times EK relationship, the error residual relationship. Um, so that's something I like to maintain. Some people will define the residual so that the error residual relationship comes out with a minus sign in one of the two locations. I find that to be deplorable and unnecessary. I also like to I also like to say the following. So the error is defined in the way that nature intended, I believe, and that is the true minus the approximation. Okay. So some people will have you believe that it's the approximation minus the true. Ultimately, it doesn't matter because you're going to take a norm of these things or absolute value of these things, and it doesn't matter. You're only interested in the absolute error. In any case, this is how we define the error and the residual. And we say that the iterative scheme converges unconditionally in if and only if the limit of the error sequence is zero. Remember, I can compute different error sequences depending on how I choose my initial vector u0. So each error sequence depends on the u0 choice. So I say it converges unconditionally if and only if the error sequence converges to zero for any choice of the u0. So this is equivalent to saying any E0, and I can compute the sequence of EKs, and the limit of the EKs as k goes to infinity should be zero. That's what we mean by unconditional convergence. Okay, any questions about that? All right, cool. So what is this B thing? So B is often what we call a preconditioner matrix or the iterator matrix. And I will say a word of warning. So there's a difference between what we did in the Purple Monster and what we do here. And in the Purple Monster, the classical numerical analysis text, you saw the iteration scheme was defined as B inverse, right? So is this different, right? So we use a B here. It's not different. It's just we're using B and B inverse in a different way. So in the book, the big purple book, this would appear as a B, not B inverse. Or no, no, sorry. In the purple book, it appears as B inverse. Here it appears with B. Okay. So this is the way we're going to use it. So just a word of warning, we don't use the inverse there. Why do we do that? Is it to confuse the students? Is it to make you guys angry? No, it's just that in the multigrid literature, this is more standard. Okay. The preconditioner matrix doesn't have an inverse on it. The iterator matrix doesn't have an inverse. The idea is B should be simple to compute, computationally inexpensive. That is going to be what? So A inverse times F, that's just U. So we get UK plus U. And then this is going to be A inverse times A times UK. That's just going to be UK, right? So if the iterator matrix was equal to A inverse, then it would converge in one step. There'd be really nothing going on there. All right, let's talk about another. So that would be beautiful, but it's impractical. Okay, beautiful but impractical. So let's talk about another extreme. Suppose I use the zero matrix there, right? Then actually nothing happens in this iteration sequence. UK is just equal to, sorry, UK plus one is always equal to UK, nothing happens. All right, that's fine. Boring, but for another reason. We could use the identity matrix, right? maybe not a very good approximation of A inverse, but that would be something as well. And the question is, well, will this give you any kind of interesting iteration scheme? Turns out this will work. Uh, it'll give you something close to what's called the steepest descent algorithm. And so it'll still work, but it's not necessarily a good thing. Okay, so if I put the identity here, then this is actually just equal to the residual. So basically you're adding on a residual to UK, and you should probably expect to get pretty slow convergence in this case. Okay, but in any case, that shows you what the kind of extreme cases will do. In the typical setting, this B matrix is just, or should be thought of as a good approximation of A inverse. It has some characteristics of the inverse, and we'll see how that goes. Any questions? Okay. As I said, this iterator matrix is also called a preconditioner matrix, oftentimes. And so in the book, in the purple book, this guy here, when I talked about B in the context of the conjugate gradient method and the steepest descent method, we didn't call it an iterator matrix there. We called it a preconditioner. Okay. So this iterator and preconditioner concept are very closely tied to each other. Okay. Now, this is especially true whenever both A and B are symmetric and positive definite. Okay. In the Euclidean sense. Now, here's another thing I want to bring to your attention. Suppose that that my initial vector u is equal to 0. Then if I look back at how things are defined, if u 0 is equal to 0, then one iteration of my general linear iterative scheme is just looks like this. And that says something kind of interesting that we're going to use later on. It says that if I apply the preconditioner to f, it's like taking one step of the general linear iterative scheme with u naught equal to 0. Okay, that probably means 0 to you now, but it's something that I'm going to bring up again later. Okay, something that I'm going to bring up again later. It's going to be a way, we're going to build this complex beast of a thing, and it's going to turn out, it's going to be a general linear iterative scheme, but it's not going to be clear it's not going to be easily deduced what is the iterator matrix. Okay, but what we're going to be able to say is, well, we don't know how to construct the iterator matrix easily, but if we set u0 equals to 0 in this complex beast of a construction, then we know it's going to be like a single application of the preconditioner. And that's the way we're going to use that fact. Remember what I said before was, that B should be a pretty good approximation of A inverse. So B times A, if B is equal to exactly the A inverse, then B times A is exactly equal to the identity. Now, what if B is just a really good approximation of the inverse of A? Then what is B times A? Well, it's something close to the identity, okay? Roughly speaking. So we say that it's a good preconditioner or good iterator whenever the condition number of B times A is small, okay? And basically, here's what that means. We know that the eigenvalues of the identity matrix are what? What are the eigenvalues of the identity matrix? It's just ones all the way down. So what's the ratio of the maximum eigenvalue to the minimum eigenvalue? 1, right? And so that's like the most perfectly conditioned matrix in all of the universe is a matrix that has a condition number of 1. Okay, so it turns out a lot of problems happen whenever our coefficient matrix has a really large condition number. And in fact, you probably remember me talking about this thing called the stiffness matrix. And we're going to get back to that a bunch in this course, the stiffness matrix. We talked about this extensively in numerical analysis. Well, the stiffness matrix turns out to have a really crummy condition number, or at least its pattern or its formula for the condition number is n gets large, where n is the number of rows and columns, gets really crappy as n gets larger and larger. It starts approaching infinity. You know, it's well, we'll discuss how it approaches infinity. Again, I'll remind you of that. But its condition number is really big. Basically, the ratio of the maximum eigenvalue to the minimum eigenvalue starts going off to infinity. And so this turns out to be pretty bad. However, we can say that a preconditioner is good if when I multiply B times A, I get something close to the identity so that its condition number is close to 1, meaning all of its eigenvalues are clustered around the same number. The eigenvalues don't have to themselves be 1, it's just they have to be basically all positive and the same number. Okay, and so that's what we're saying here. That if I can find a preconditioner such that B times A has a really tight clustering around a single number, let's say 400. So the smallest one is 400, the biggest is what? 401. Or maybe more practically, the smallest one is 399 and the biggest one is 401. That's a ratio which is pretty darn close to 1. So we'd be happy with that. So that's what we mean by finding a good preconditioner. It's like finding a needle in a haystack. So I'm going to teach you how to find good preconditioners in this course. That's another thing we're going to talk about. I just wanted to remind you one more time, just in case you had forgotten, that this matrix, this product matrix, B times A, is going to be symmetric and positive definite with respect to either this inner product or this inner product, but its product itself is not necessarily even symmetric with respect to the Euclidean inner product, right? So that's just something to keep in mind. All right, now let's construct an error equation, shall we? Okay, we have the simple error residual relationship we defined before, but let's define something more. So it's easy to see that the true solution is a fixed point for our general linear iterative scheme, right? So let's see why. Well, what happens if I put in the true solution over here for UK? What do you get? Well, F minus A times U is equal to what? What would be F minus AU if I put in the true solution? And so that's just saying that U equals U. That's what we call a fixed point for this iteration scheme. So the true solution is a fixed point for the general linear iterative scheme. Does everyone see that concept? It's a pretty easy one, right? Now, besides that, we have the definition for the scheme. And I said it's different than what we had in our previous book slightly because there's no inverse here. It's naked without the inverse. Okay, so now take this equation, and from that, we're going to subtract this equation. Okay, we'll do term by term subtraction, use the linearity property, and what do we find? Well, what we find is that we get EK plus 1. That's what we would get by doing this minus that, EK plus 1. This minus that is going to give me EK. And then I'm going to have BAEK for this minus that. You can check that that works. B times F, that cancels, right? And so I just get this term. It turns out that's just minus B times A times EK. And I can cluster this together by pulling out, using the distributive property, this vector EK, and I get I minus BA times EK. So in the previous book, that would have been B inverse, but here it's B. Okay? So now that matrix appears so often and is so useful to us, we're going to give it a name. So we're going to call that the error transfer matrix. Suppose that A is invertible, F is given, U is the true solution, and UK is the kth iteration step for my linear iteration process. then the GLIS error transfer matrix, which we call T, is defined as I minus BA. And if it's I minus BA, then it's not too hard to see that EK plus 1 is equal to T times EK. So why do we call it the error transfer matrix? Well, it transfers the error from the previous step to the current step. That's it. It transfers the error from the previous step to the current step. And it turns out that knowing what this guy looks like and what are its properties, especially its eigenvalue properties, will help us determine when this general linear iterative scheme is going to converge. All right? So that's where we'll pick up next time. We'll talk about the spectral convergence theory. And in fact, most of you guys know this, at least a large section or segment of this population knows this stuff all too well because you just studied it for a prelim. And for the rest of you, it's just going to be a little reintroduction or reminder of what's going on. So that's where we'll pick up next time. Are there any questions? If not, then I will see you on Thursday. You can email me if you have any questions. I'm here in the lovely Ayers Hall, room 239. You can stop by when I'm around, usually on Tuesdays and Thursdays, hopefully with some regularity. Other times by appointment. And I am going to set up a Zoom office hour at some point. And so if you need to make use of that, you can. But the best way to reach me, as always, is going to be via email. Okay, so if you have any questions, let me know. And otherwise, I'll see you guys next time and have a great day.